This morning I am embarking on what I hope will be a useful series. There is a book called The Art of Electronics, and this is a lab manual for that book. Now, the original book I commend to you. It's a very good, useful text. In fact, if you're going to have one book on electronics, I would suggest The Art of Electronics. This is the lab manual. It's called a hands-on lab course. What I'm going to do is pick a few of the lab exercises from this book and try to illustrate them using the analog discovery. Well, one of the first ones in the book is a power supply that is shown there. So, I have gathered some parts, a transformer that you show on the left here. This shows a full wave bridge. We'll get to that and we'll talk about that later because I want to use this as an illustration of power supplies. So I'm going to do first a half wave and then later a bridge or full wave rectifier. And one of the things that I'm going to have to do is, if you see on here, I need to attach a power cable here. So I've stripped a cable here, and for those of you that watch my videos, you may say, boy, he's going a lot slower than he normally does, and that's really the purpose here. Because this is intended for somebody who might be a beginner or at least only has a little bit of experience, I'm going to show a little more technique than I normally do. So, one of the first things I did is I stripped off the insulation, and this is the tool I used for that. It's fairly readily available. There are much fancier tools, but I'm going to try to stick with basic stuff. For safety reasons, I'm going to be putting some heat shrink tubing on the connections. And I've gotten out a fairly cheap soldering iron deliberately for the purpose of illustrating. What I'm going to be doing now is what's called tinning the tip, which involves putting some solder, some rosin core solder on the tip. The purpose is to remove as much of the oxidation from the tip as possible and to coat it with a rather protective coat. And I'm doing this with a fresh soldering iron. This is one that I've owned for a while but have not ever used before. So you may be able to see that what we've done is we've tinned the tip. Now that we've done that, we're prepared to start assembling this. So the next thing I'll be doing is cutting some heat shrink tubing for the cable and soldering it to this. I won't show you that. I'll assume that you are either already have some experience with soldering or that you can look at some other YouTube videos on those sorts of things. I suggest a variety of individuals, Dave Jones with the EEV blog and some of his videos on soldering and so on. So at any rate, let me get that started, and I'll come back when I'm ready to finish up on the primary of the transformer. Now I've soldered the wires to the primary of the transformer. Then what I'm going to do is slide this shrink wrap tubing over the ends to make sure these are insulated so that if I accidentally touch this side of the transformer, I won't be able to contact the AC line. And this is very important for safety reasons. You make sure that there never is a way that you can make a mistake and come in contact with the AC power line. And so throughout this series, I'm going to be emphasizing safety, and I hope you won't take it as treating you as dumb. It's just that there have been times in my life when, even though I knew better, I made some mistakes that could have killed me. I was fortunate. Some people are not. I certainly don't want anybody to even take those chances, and especially not if they have the consequences that they can have, which of course is serious injury or even death. So I'll slide these over, and then I'll show you how that I shrink that tubing down. Now I'm going to shrink the tubing on those wires, and I'm going to use a soldering iron to do that, and I'll just show you a little bit of that. Now there's a better way to do this using a heat gun. One reason I want to use a soldering iron is to show people who maybe can't, don't have access and don't want to buy a heat gun, how to do it. The second reason is when I turned on my heat gun this morning, it didn't work. So I'm going to have to find out what's wrong with it. So at any rate, here is a way to shrink tubing using a soldering iron. Now, I don't use the tip of the iron. I use the shaft. And if you gently rub around the wire using just the heat of the shaft, you'll find, and one of the reasons that I don't use the tip is I don't want to remove that solder plating that I put on the tip. I'm just using the heat, the residual heat in the shaft to heat the shrink wrap tubing. And what that will do, by the way, for those of you that don't know about this stuff, it was invented during the space program in the 60s. The way it works is they take a particular kind of plastic and they irradiate it with an ion machine or a particle accelerator to irradiate it. And what that does is it causes the molecules to assume a kind of tension. And then when you release that tension with heat, the molecules shrink up. And so that's how this stuff works, if you ever wondered. Okay, so now we've got a fairly safe transformer. We have a primary with 120 volts, and hopefully everything there is insulated. And then over here on the secondary, 12.6 volts. So the next thing we're going to have to do is put some leads on the secondary so that we can start wiring this up. And I'm going to do it on a breadboard. So that'll be the next segment. So of course, one of the first things we're going to need to do is have a way to make some measurements. And I am going to be using this device. It's called the Analog Discovery 2. I'm sure that many of you are already familiar with it. It basically is an oscilloscope, as it says in the upper right-hand corner there. Don't be fooled by the 100 ms per second. That's not 100 megahertz, that's 100 megasamples per second. The actual frequency response of this scope, depending on how you use it, is somewhere between, say 15 megahertz and 30 megahertz. With the right accessories, it'll go near 30. It also has a logic analyzer, variable power supply, various a couple of waveform generators, at any rate, a number of things. So it's always a good idea to take a look at the specifications. So we'll run down here and you'll see that the oscilloscope, it says it's a 2-channel. I'm reading there at the right under the features section. A 2-channel USB digital oscilloscope. 1 megohm, that's the input impedance, plus or minus 25 volts differential. Now later we'll find this is beneficial, differential. But you need to start wondering, 25 volts, that means plus or minus 25 volts means a maximum of 50 volts peak to peak. In other words, is this going to be a problem? Well, if you remember, our transformer says it has a 12.6 volt output. So shouldn't be a problem, right? Whether that 12.6 volts is peak to peak or it's half of that, in other words peak, which by the way that is supposed to be peak to peak, but as we'll find out later, you can't really believe these numbers. You can't really believe this number, and you can't really believe that 12.6 number written on the transformer. So let us fire up the analog discovery and hook it up to the output of that transformer and see how much voltage we see. So one of the first things you have to do when you get an analog discovery is you have to download a piece of software called Waveforms from the Digital website. Once you've downloaded it, then you connect the analog discovery and you fire it up, and this is the first screen you see. Up here it says Waveforms, and along the left it shows some of the various features or functions that you can perform. We're going to initially be interested in this one here, scope. And remember it said it is a 2-channel oscilloscope with a megohm input and plus or minus 25 volts for its input rating. So let's start up a scope. And I'm going to move the oscilloscope here. I'm going to expand its size a little bit. And I'm going to turn off channel 2, and I'm going to set channel 1 to 5 volts per division. And I'm going to set the time base to 5 milliseconds per division, and I'm going to click on Run. Well, now we've got a waveform, but let's take a look at that waveform. Doesn't really look like a pure sine wave. We notice a couple of things. One, there's a little bit of an anomaly here where the waveform seems to go from a sine wave to almost a triangle wave or whatever. But more important, the tops look like they're rounded off, and so are the bottoms. Now, we have this set, and on the left you see what the scope, well, maybe you can't see that too well. Let me zero in on that. You see on the far left it says that this top is 25 volts. And remember it said plus or minus 25 volts. So what's going on here? Well, the reality is that the analog discovery, the 25 volts, is the maximum signal you can apply. In other words, that's the safe range. But it really won't quite display a 25 volt signal. At least mine won't. When you get much above 20 volts, the analog discovery begins to limit. That is, it begins to compress. So, okay, that's not good. Also, remember we said 12.6 volts was the rating on the transformer? Well, that's 12.6 volts RMS, and that's with a load. Normally, in this case, the transformer is rated at 300 milliamps, so maybe that's at 100 or 150 milliamps load. Without a load, you get a lot more voltage. So instead of 12.6, which would be about here, in the first place, that's RMS. So you have to multiply by 1.414 to get peak. And you'll find that the peak comes out about just under 20 volts. So why is it going all the way to 23 or 24 volts? Well, it's because it's unloaded. So we have two problems. One is we need to load the transformer. And the second thing is we need to find a way to display the full output. The second approach involves the addition of an accessory that does not normally come with the analog discovery. So let me show you that. Here is the analog discovery connected with the fly wires that it comes with. In other words, if you buy just the analog discovery, it comes with a header and a bunch of fly wires. Now you'll notice here there's a clip, and those you can buy extra, but they don't come with the analog discovery. And then in the upper right hand corner you see the transformer with the 12 volt primary connected here, and then the channel 1, that is the two orange wires of the analog discovery, connected using a little breadboard. So what can we do to increase the input range of the analog discovery? Well, we add a board that's also sold by them, and the board is this one. It's basically a BNC adapter board. In other words, this plugs into the analog discovery, and then on one side you have a pair of BNC connectors for the oscilloscope, and on the other side you have a pair of BNC connectors for the waveform generator. So let's hook that up. Now we've connected the BNC adapter board to the analog discovery, and we've connected a 10x scope probe to the input. Now by 10x, what we mean is that it divides the input signal by 10. So the 25 volt signal that we had before, or 23, is now a 2.5 or 2.3 roughly volt signal peak. So let's see what that looks like on the analog discovery, or on the waveform software. Well, that's a little more like it. Seems to have eliminated some of that distortion. But let's go down now to, let's say 1 volt per division, and understand that really means 10 volts per division. You notice we still have that flat topping, and we still have the problem here. Well, earlier when I was explaining to you about the limitations of the analog discovery, I was really fooling you in a way, because the truth is most of this flat topping and this nonlinearity here is actually due to the fact that we're using a very cheap transformer. What's happening is that the core of the transformer is actually getting saturated here, and this part is, well, it's called the hysteresis curve, but let's not get too technical. Basically, it's how easily you can magnetize and demagnetize the core. And of course, when the signal is in the negative direction, the core is magnetized in one direction, and then it has to switch directions when it goes here. And as it switches from one direction to the other, it goes through a very nonlinear part of its curve. And so that's what's really going on here. So why did I pretend that it was the analog discovery's limitations? Well, the reason is you need to be careful that you are aware of the limitations of your test equipment. If you don't understand the fact that the analog discovery without a by 10 probe can only display a 25 volt signal, you're likely to hook it to something like the 120 volt AC line, in which case you can go to the website and put in another order for another analog discovery, because chances are you fried yours. So be careful, read the specs, and use this with care. Just as in the first part of this video, we talked about the importance of insulating the AC line, you don't want to apply large voltage signals to the analog discovery unless you know you have that you're operating it within its prescribed parameters. So okay, we got a cheap transformer. It doesn't really produce this kind of thing. We're not going to care about that too much because we're just trying to produce some DC voltage out of it. So let's move on to doing that. So on the breadboard, I've implemented the circuit you see here. On the left is the transformer, 110 volts on the primary, 12.6 volts on the secondary. And then channel 1 of the analog discovery is connected across the secondary. I've also put a 1.5K resistor. That's to keep the impedance fairly constant. Don't need to worry about that for now. It doesn't draw very much current. Then a diode, a 1N4005 in this case, but this can be almost any diode as long as it's sufficient to handle the current and that you're going to be drawing. And not much out of this supply anyway. And then a 1.5K ohm resistor on the other side. So what this is doing is the diode effectively is an open circuit when the top of the transformer is negative with respect to the bottom. But when the reverse is true, that is when the top is positive with respect to the bottom, current flows through the diode and down through the resistor, producing a voltage drop across the resistor. So let's take a look at that on the analog discovery. And here you see channel 1 in yellow, that is the secondary of the transformer, the 12 volt AC. And in blue is the output of the diode. So let me turn off channel 1. And you can see what we've produced is a DC voltage. That is, we have turned this cycle, half cycle, into a positive pulse of current, thereby generating a net DC value somewhere in here. But when it goes negative, we have cut it off. This is what is known as a half-wave rectifier. A half-wave rectifier simply means it's operating on half of the input wave, and it is rectifying, in other words, straightening out, converting a signal that is going in both directions into a signal that only goes in one direction. We will take this pulsed DC value and try to smooth it out. That is, try to produce a DC value by filling in this area in between with some kind of charge storage. Most of you already know what that's going to be. It's going to be a capacitor. So we're going to put a capacitor in, and that will hold a charge. In other words, the capacitor will charge up to here, and then will slowly discharge down, recharge again, slowly discharge, and so on, thereby providing a smoother DC voltage. Now we've placed a capacitor across this resistor. The capacitor is a 10 microfarad, 35 volt capacitor. So let's take a look at what that has done to our waveform. As we see, it has smoothed it out somewhat. What used to be a pulse that started here and went up and came back down to here and then was flat and then went up and came back down. Now we are filling it in. We're only filling in about half of it though, because the droop, that is the amount of voltage drop from the high to the low, is about half of the total. And that's because we're only using a 10 microfarad capacitor. So let's put a bigger capacitor in and see if we can maybe get a little better performance, that is less droop in the output. And here is the same circuit with a 47 microfarad capacitor. Notice that now we're getting a relatively constant DC voltage. Now, the amount that the output deviates from a pure DC level is called the ripple. And in this case, the ripple is relatively minor. Now, this would not be an acceptable power supply for any kind of precision circuit. It would probably work okay to power a transistor radio or something of that sort. But if you were looking for a nice clean source of DC power, a simple half-wave rectifier with a simple RC resistor capacitor filter is not really the way to go. And as we'll probably see in some future video, the way to get a better output is first to use a full wave rectifier. We may do that in the next video or not, depending on the response. And then maybe in a future video we'll introduce the idea of voltage regulation, where you can get an almost perfect DC value, at least up to a certain current level. And in that case, you do have a signal that is satisfactory for use in more critical circuits. So I'm now going to reconnect channel 1 so you can get an idea of what we've done. We took this pulse and converted it into a relatively flat DC value, and we have cut off this pulse so that it plays no part in the output. That is a simple half-wave rectifier with an RC filter. I hope this is interesting enough. It's intended to be a very introductory idea. It's partly to introduce people to the analog discovery and partly to get them started experimenting with some simple circuits. So if you've enjoyed this, let me know. If there's not a lot of response, well then I'll probably assume that maybe I should go on to some other topic. But if there is a reasonable amount of response to this, what I intend to do is to continue this series, working my way through that Art of Electronics lab book as we go. So let me know, and if it's something that you're interested in, at this point it may be a little bit simple for you if you have some experience, or it may be exactly what the doctor ordered if you're somebody just starting out. But in either case, I hope you've enjoyed this. Hope you'll look forward to some more. And in the meantime, have a nice day.